Welcome to the Sleepy Scientist. If you're watching this, you're probably ready to relax, slow down, and gently drift into sleep while staying a little curious. Tonight, we're going to explore one of the quietest and strangest parts of science, the weird world of matter. From solids that don't act like solids to crystals that seem to move with time, we'll take a calm and gentle trip through how tiny pieces of stuff behave. Hopefully, this video won't be too interesting, because that might keep you awake, and that's not the plan. But even if you're still awake by the end, you'll have learned something cool. Like how some solids can flow, some liquids act like crystals, and how many things don't seem to follow the rules but still make sense in their own way. It's like a bedtime story only science could tell. Before we begin, if you enjoy this calm look at science, I'd be really thankful if you clicked like and subscribe to help this little peaceful channel grow. And if you feel like it, let me know in the comments where in the world you're listening from and what time it is. I like to imagine our little worldwide campfire of sleepy minds, from quiet country towns to busy midnight cities, all connected by a shared sense of wonder. This video is made to relax you and gently amaze you. Don't worry about remembering facts. Just float along as we talk about matter that moves, shifts, and surprises us. It might sound like magic, but it's all science. Also, just a note, this video is for relaxing and learning only. It's not medical advice or a replacement for real care. Always take care of yourself and sleep well. So, what is a solid? It seems like an easy question. A solid is something that keeps its shape and doesn't squish unless you press really hard. A rock, a spoon, a table, they're solid, right? But hold on to that thought carefully, because even the idea of a solid is a lot more slippery than it seems. In basic science, we're told there are three main states of matter: solid, liquid, and gas. You may have seen a simple drawing in school showing this. Solids stay in shape, liquids flow, and gases spread out. That's just the start of the story, and some scientists think this view is too simple. In the classic view, solids don't change shape or size. Their atoms are packed in a neat, repeating pattern, like a crystal. These atoms can shake in place but don't move around. Liquids don't have a fixed shape, but their volume stays the same. Their atoms are still close but can slide past each other. Gases, on the other hand, have atoms that are far apart and move freely, filling up any space. This neat system helps explain everyday stuff. Ice is solid, water is liquid, steam is gas. It makes sense if you're cooking or teaching kids. But the universe doesn't always follow simple rules. Now let's look more closely at solids. Even within the things we call solids, things get messy. Some solids, like glass or volcanic glass, don't have neat atomic patterns. Their atoms are jumbled, more like a liquid that froze before getting fully organized. These are called amorphous solids. They look and feel solid, but at the atomic level, they act more like really slow-moving liquids. So, being solid isn't a strict rule, it's more about how stuff behaves. And that's something we keep seeing in science. The lines are blurry. Take pitch, a thick black substance. At room temperature, it looks totally solid. You can knock on it. But if you wait long enough, it flows. There's even an experiment that started in the 1930s where a blob of pitch was left to drip. It takes about 10 years for a single drop to fall. That's slow, but it still flows. So is it a solid or a liquid? Meanwhile, liquids and gases can mix into each other too. There's not always a clear line between them. Under certain temperatures and pressures, materials enter a supercritical state. This state has traits of both gas and liquid. It can spread out like a gas but dissolve things like a liquid. At that point, even the tidy chart we learned in school doesn't quite work. But wait, there's more. If you heat or cool things enough, you find even more phases of matter. These aren't just rare exceptions. They're real and often common. Plasmas, for example, are in lightning, the sun, and neon signs. Some call plasma the fourth state of matter, but actually, scientists have found many different states depending on how you look at things. Some materials change under pressure, others under electricity or magnets. So why do we even try to label matter? Well, because humans like organizing things. It helps us understand a world that doesn't like to stay the same. The state of matter depends on how molecules act and how much energy they have. Temperature and pressure control a lot of it. Add heat or squeeze something, and its state can change. But in extreme or quantum situations, the rules bend, or do flips. One good way to understand matter is to think about how it changes, those in-between moments when things melt, freeze, boil, or condense. That's where the exciting stuff happens. Molecules start to move in new ways. Structures shift. Properties change. Something hard becomes slippery. Something fluid becomes solid. Even breathing shows this. On a cold day, your breath becomes a little cloud. The water vapor in your breath turns into tiny drops in the air, floating before disappearing. That's a transition caught in action. A quiet reminder that matter is always ready to become something else. The three states we all learn about are like the surface of the ocean, clear and easy to see. But under the surface is a deep, changing world of molecular action. Sometimes it's tidy. Sometimes it's a mess. Sometimes it's not what we expected at all. That's how nature works. It doesn't have to be simple, just consistent. And even that consistency is in a language we're still figuring out. It feels nice to think of solids as strong and stable, but that's more about how we feel than how they work. In the tiny world of atoms, being solid can just mean something hasn't changed yet. Wait long enough or shift the conditions, and it might not seem so solid anymore. Matter, in a way, is like us. It goes through changes. It holds together until something makes it shift. And sometimes, it ends up in a state we haven't even named yet, waiting for someone curious enough to notice. If you've ever seen an old church window or passed a very old building with strange, wavy glass, you might have heard something odd. People say the glass flowed over time, slowly sinking because it's not a real solid. It sounds mysterious, like a secret from science. Some say glass is just a super slow liquid. It's a cool idea, like something from a science storybook. But as much as we like that idea, it's not really true. At least not the way most people think. Let's go back to the basics. Glass is what scientists call an amorphous solid. Unlike crystals like salt or diamonds, it doesn't have a regular atomic pattern. If you zoomed in on quartz, you'd see a nice, tidy grid of atoms. Every atom has its spot. But in glass, atoms are random and messy, more like a liquid that suddenly froze before getting organized. They're stuck, but they aren't in order. It's like a busy room where everyone stopped moving mid-sentence. This lack of structure makes glass behave in special ways. It's hard like a solid, but not ordered like a crystal. Its atoms still wiggle in place, but they don't settle into a repeating pattern. It's like a party that paused but never ended. Now back to those old windows. The idea that they're thicker at the bottom because the glass flowed is a popular myth. But the real reason they're uneven is how glass was made long ago. People used methods like spinning glass into circles or forming long tubes and flattening them. That created uneven sheets. When people installed them, they usually put the thicker side at the bottom to keep them stable, not because the glass was melting, but because it made sense. Today, when scientists check these old windows, they find the thick parts aren't always at the bottom. Sometimes they're at the top or sides. If the glass had really flowed down over time, we wouldn't see that. Plus, the amount of time glass would need to visibly move at room temperature is longer than the age of the universe. That's not exactly something we can test. But here's the fun twist. The myth has a little truth in it. Glass doesn't flow in everyday life, but it does act like a very slow-moving liquid when it's hot. That's why you can shape it when it's melted. It's like thick syrup at high temperatures. And even when it cools and looks solid, glass never fully becomes a crystal. It's like a material that's paused in the middle of becoming solid, stuck in a moment of change that never really ends. Scientists use a term called the glass transition to explain this state. Unlike melting or freezing, which happen quickly at a set temperature, the glass transition is a slow process. As the material gets colder, its molecules move slower and slower until they seem frozen. But there's no clear point where it changes. It's more like watching people slowly fall asleep without one exact moment of silence. Pitch is another strange example. It looks and feels like a solid and breaks if you hit it, but over many years, it moves. A famous experiment that began in 1927 shows this. Scientists placed pitch in a funnel and waited years for a single drop to fall. It's technically flowing, just extremely slowly. This slow movement over time doesn't only happen in pitch or glass. Some plastics and even metals can act this way in the right conditions. They don't clearly fit into the normal categories of solid or liquid. They remind us that the state of matter sometimes depends on time rather than strict rules. Obsidian, a shiny black rock made from cooled lava, is another example of this disordered structure. When lava cools fast, it doesn't have time to form crystals. Obsidian looks and feels solid and is sharp enough for surgery tools, but inside, it's just like glass. Its molecules are messy and out of order. Nature doesn't always wait to make things neat. What makes all of this even more interesting is how it goes against our instincts. We decide if something's solid by touching it or looking at it. If it clinks when we tap it or breaks when dropped, we say it's solid. But molecules don't care what it feels like. They follow their own rules based on motion and energy. When those rules land between solid and liquid, the material becomes both and neither. There's something quietly beautiful about these materials. They look still, but they're not completely still. They seem structured, but that structure isn't finished. They don't scream for attention, they show complexity in a quiet way. A window, a chunk of obsidian, or a drop of pitch, all show us that the universe doesn't rush to label things. Sometimes it just stays in between. And instead of thinking glass is just a stubborn liquid pretending to be a solid, it's better and more accurate to see it as something special, not a failure, but a different kind of order. One that accepts being a little messy as part of its nature. In a world that often wants clear answers and neat boxes, glass teaches us something else. It reminds us that matter, like time, can move quietly between the lines. If you asked most people to name the states of matter, they'd probably say solid, liquid, and gas. Maybe one would pause and say, "Oh wait, what about plasma?" And they'd be right. Plasma often gets left out like a forgotten cousin who only shows up for big space events. But the truth is, plasma isn't rare at all. It's actually the most common state of matter in the universe. Not here on Earth maybe, but out in space, it's everywhere. Stars, the sun, nebulae, and even the glowing lights near the North and South poles, all powered by plasma. Plasma is basically a super-energized gas. It happens when atoms get so much energy that their electrons break away. Instead of being neutral, you get a mix of positively charged ions and free electrons zipping around. This changes everything. It no longer acts like a gas. It becomes something new, something that reacts to electric and magnetic fields. It glows, it pulses, and it can even twist into odd shapes in space. It all starts with energy. Add enough heat or electricity, and atoms lose their balance. Normal gases have equal protons and electrons. But in plasma, that balance is gone. Now, it can carry electricity, create magnetic fields, and support strange behaviors like waves or threads of glowing light. We don't see plasma much on Earth, which is why people don't think about it. But it is here. Lightning is a quick burst of plasma. The sun's surface is made of it. And even things like neon signs, fluorescent lights, plasma TVs, and some welding tools all use it. That buzzing glow in neon signs isn't just a light, it's plasma giving off energy as excited particles bounce around. Plasma is different because of how it responds. Unlike gases that just float freely, plasma listens to magnetic forces. It can be shaped, guided, or trapped in certain ways. In labs, scientists use strong magnets to hold plasma in donut-shaped machines called tokamaks. They do this to try to make energy like the sun through fusion. It's like catching lightning using magnet nets. Plasma can also create beautiful natural displays. One of the most amazing is the aurora borealis, the northern lights. When charged particles from the sun hit Earth's magnetic shield, they're pulled toward the poles. There, they hit gases high up in the air and make plasma light shows. The colors, green from oxygen, purple and red from nitrogen, happen because the atoms get excited and then calm down, releasing light. It shows us Earth is wrapped in a magnetic hug, and plasma is quietly shining above us. But plasma isn't just for beauty. It also causes huge events like solar flares and blasts from the sun's surface called coronal mass ejections. These waves shoot particles into space. When they reach Earth, they can mess with satellites, knock out power, and light up the sky with even brighter auroras. It's like the sun sending out a powerful sneeze, and we feel the effects. Beyond our solar system, plasma fills the space between stars and galaxies. The glowing spiral arms of galaxies and bright clouds in space, all made of plasma. It's not rare at all. It's the main state of matter in the universe. If you counted all the atoms you could see, most of them would be in plasma form. The universe seems to love electrified things. Plasma also has real uses. It's used in machines that cut metal with precision. It's being tested in spacecraft engines for faster space travel. Even some tools in medicine use plasma to clean and change materials at tiny levels. It's the kind of science that sounds like fiction but is becoming real. Still, plasma doesn't always follow simple rules. It doesn't behave like solids, liquids, or gases. It does its own thing. It can twist, spiral, and move in strange patterns. Scientists use powerful computer models to understand it. One thing they study is magnetic reconnection, where magnetic fields break and reconnect, releasing a ton of energy. This may be what causes solar flares and other space explosions. Plasma can also get extremely hot. The sun's surface is about 6,000 degrees, but its outer layer, the corona, can hit several million degrees. Why the corona is hotter than the surface is still a mystery, but plasma is likely the key. It shows that even something as familiar as the sun hides secrets. Plasma also breaks the neat order we like. It teaches us that adding energy doesn't just heat things up, it can totally change what the material is. A gas doesn't just get faster, it becomes something brand new, something with magnetic powers and glowing shapes that stretch across space. That's why plasma challenges how we think. It shows us matter isn't just solid to liquid to gas to plasma. It's a shift into a different world with different rules. That's worth thinking about. It reminds us matter is always changing. Its behavior depends not just on temperature or pressure, but on how its particles and forces interact, from tiny atoms to massive galaxies. Whether glowing inside a sign or burning on a star, plasma is matter that lights up possibility. It's the often forgotten fourth state, a shining thread woven through the universe. Now imagine taking a group of atoms and making them really, really cold. So cold that they almost stop moving. As their temperature gets close to absolute zero, the coldest temperature possible, their motion almost stops completely. Then something amazing happens. The atoms stop acting like separate things and start behaving as one. Not just like they're working together, but literally becoming one single quantum state. They lose their individual identities and act like one big wave. This is called a Bose-Einstein condensate, or BEC. And it's one of the strangest and most incredible forms of matter we've ever found. To understand why it's so cool, we need to talk about quantum physics. At this tiny scale, atoms don't act like small balls. They act like waves. Each atom has a wave function, a sort of mathematical ghost that tells us where it might be and how it might move. Usually,